Morning, dear students. Welcome back. So today's topic of discussion is states of matter. So we are going to discuss the topic states of matter. So matter, okay. So matter is made up of different types of atoms and molecules, right? So matter, it consists of mainly, or states of matter, it is been divided into three types: solid, liquids, and gases. So here you will be mainly studying about gases. Okay. So what are these intermolecular forces? Okay. There is something called as intermolecular forces. So intermolecular forces are the forces of attraction and repulsion between the interacting particles. Okay. So these are the forces which are acting between the interacting particles. So the attractive forces are called to be van der Waals forces. So these intermolecular forces are further divided into three forces: dispersion, or they are said to be London forces, then dipole-dipole forces, and the third, dipole-induced dipole forces. So we'll see each force separately. Okay. So what are this London or dispersion forces? So these are exhibited by non-polar molecules. So in the last class, we had discussed what are polar molecules and what are non-polar molecules, right? So what are non-polar molecules? The atoms are of same the molecules are made up of same atoms. Okay. So these London forces are exhibited by non-polar molecules because of temporary correlated movements of electrons in interacting molecules. Okay, you can see here in the step 1. So what is happening here? So there is symmetrically the charges are distributed. Okay, so this force is temporary. This force is temporary. Okay, and these forces are always attractive. You can see there is symmetrical distribution of positive and negative charges. So there will be the forces are always attractive. So the interaction of this energy is inversely proportional to 6th power of the distance between the two interacting particles. So the interaction energy here is inversely proportional to the 6th power of the distance between two interacting particles. Okay, so here you can see atom 1 and atom 2, right? So these are two different atoms. So you can see positive charge and one side negative charge. So your negative positive, there is an attractive force. So this is nothing but your London forces or dispersion forces. And these forces are only applicable for short distances. Okay, if the atoms are nearby, so then only these forces are applicable. If the atoms are very far, then these forces are not applicable. Okay, and the magnitude of this particular forces, it depends upon the polarizability of the particle. So what do you mean by polarizability? To distort the, okay, it distorts the structure. It distorts the structure. Okay, so its magnitude, it depends upon the polarizability of the particle. So these are called as London or dispersion forces. So this is a first type of intermolecular forces. Then second is dipole-dipole forces. Okay. So these dipole-dipole forces act between the molecules which possesses permanent dipole. Okay. So last class we had discussed about dipole movement also. So where does dipole or dipole movement is considered? When you have a polar molecule. Okay. What do you mean by polar molecule? When one of the electronegative atom is attached. Okay, when one of the electronegative atom is attached, so what happens? Electronegative atom, as a result, it tends to pull the electron towards itself. So as a result, you can see here, okay, as a result, what is happening here? You can see partial negative and partial positive charges are developed. So this is nothing but partial charges are developed. So you can see the dipole moment, it acts between the molecule possesses the permanent dipole. So the end of the dipole possesses partial charges. So these are nothing but partial charges. So end of these dipoles, they are having partial charges. Okay. So these partial charges are always less than the unit electronic charge. So the partial charges are always less than the unit electronic charge. Then these interaction is stronger than London forces. Here the dipole moment or dipole-dipole forces are stronger than the London forces, but they are weaker than the ion-ion interaction. Okay, ion-ion interaction, it is weaker. Why? Because in this case, in dipole-dipole forces, you can see there are development of partial charges, but in ion charges, directly the interaction will be between the two ions, right? So here there are partial charges are there. So because of that, the ion-ion interaction is more stronger than the dipole-dipole forces. Okay, the attractive forces decreases as there is increase between the dipoles. So as this dipole are this dipoles are separated or they have taken far away, what happens? The attractive forces keep on decreasing. Okay, it goes on decreasing with the increase in the distance between this dipoles. So here, how is the interaction energy given? So the interaction energy between the stationary polar molecules is proportional to 1 by r cube. Okay, so it is proportional or it is inversely proportional to r cube. Then this interaction energy between the rotating polar molecule is double of the stationary polar molecules. Okay, and here r is nothing but your distance. So you can see here. So these are two dipoles in the first picture where you can see there are two dipoles. Okay, this is having blue side, it is having partial negative charge, and the red side, it is having a partial positive charge. So here, like unlike charges, they attract each other, and like charges will repel each other. So there is an attraction between this. The first picture depicts that there is an attraction between the dipoles. Then second, you can see, right, the red side are on same side. So that is nothing but it is both are partial positive. So like charges, they will repel each other. So there is a repulsion. So always the dipole forces or dipole forces are formed between the polar molecules. Okay, and it is due to the what is happening there. There is a development of partial charges. So this is about dipole forces. Next is induced, okay, dipole induced dipole forces. Now what do you mean by dipole induced dipole? Okay, one of the atom will be having a permanent dipole. Okay, there will be a development of charges, and another will be a non-polar molecule. So consider here one we have taken. So you can see here, okay, you can see here, this is a molecule which is having a polar. Okay, it is a polar molecule. Polar molecule means what? There will be a presence of negative electronegative atoms. So as a tendency, what will happen? It will tend to pull the electron towards itself. So as a result, there will be development of partial negative and partial positive charges. Okay, as you can see here. So there is a permanent dipole on this particular molecule. Okay, it is a polar molecule. And so this is a dipole molecule. Then this is the second one. What you can see, it is a non-polar molecule. Non-polar molecule means what? The molecule made up of same atoms. Okay, so there will be no separation of charges because both the atoms will be having same charge. So what we are doing by introducing this dipole polar molecule, we are going to induce its dipole on this non-polar molecule. So it is called as dipole induced dipole forces. Okay, so what are the characteristics of this dipole induced dipole forces? So this type of attractive forces, it operates between what? It operates between a polar molecule which is having a permanent dipole and the molecule which is having or which is lacking the permanent dipole. Okay, so it is between a polar molecule and a non-polar molecule. So the interaction energy, how is the interaction energy given? It is inversely proportional to the 6th power of the distance between the two interacting particles. So this is also inversely proportional to the 6th power of the distance between the two interactive particles. Okay, how is this induced dipole moment? It depends on what? It depends on the dipole moment which is present on this particular permanent dipole. Okay, so this induced dipole, so this non-polar molecule, it depends on what? It truly depends upon the magnitude of the dipole moment which is present on this particular permanent dipole. Okay, and the polarizability of the electrically neutral molecule. Then the molecules of larger size can be easily polarized. So whenever you are taking the molecules of larger size, so they can be easily polarized. Okay, so higher the polarizability increases the strength of attractive interactions. Okay, So as you introduce the molecule which is of larger size, so greater will be the attractive forces. So this is nothing but your induced dipole. So you can see clearly. So one of the molecule will be a polar molecule, another will be a non-polar molecule. So what you are going to do? So on a polar molecule, as there is an electronegative atom, so there will be separation of charges. You can see partial negative and partial positive charges are there. So when this non-polar molecule is introduced, okay, so this dipole movement is induced on this non-polar. So as a result, you will able to see this. Okay, so this is a permanent dipole. Okay, second your permanent dipole with a polar molecule, and so this is induced on a non-polar molecule. So the charges get induced. So these are the three types of interactive forces. Okay, internuclear forces. So based on this, we'll solve some of the questions. Okay, which of the following is not a type of van der Waals forces? Yes, we have discussed about this. So which one of the following is not a type of van der Waals forces? A, dipole-dipole forces. B, dipole-induced dipole forces. C, ion dipole forces. Or D, London forces. Yes. Which is not a type of van der Waals forces? It is C. Okay, C is the correct answer. So ion dipole forces. Ion dipole forces is not a type of van der Waals forces. Okay, so this is the correct answer. So it is C. Ion dipole forces. Who proposed the concept of dispersion force? Who proposed the concept of dispersion force? Dispersion force is nothing but London force. Okay, the another name for dispersion force is London force. So the scientist who introduced the concept or proposed the concept was Fritz London. Okay, so the option is D. Fritz London. Next, the interaction energy of London force is inversely proportional to 6th power of the distance between two interacting particles, but their magnitude depends upon. Yes. So what is the answer? The interaction energy of London force is inversely proportional to the 6th power of the distance between two interacting particles, but their magnitude depends upon. On what does the magnitude depends? The magnitude will depend upon the polarizability of interacting particles. Okay. C. Polarizability of interacting particles. So the correct answer is, so the magnitude of this London force depends upon the polarizability of interactive forces. Next, dipole-dipole forces act between the molecules possessing permanent dipole. Okay, then ends of dipole possess partial charge. The partial charge is A, more than unit electronic charge, B, equal to unit electronic charge, C, less than unit electronic charge, D, double the unit electronic charge. Yes, what are the characteristics? It is less than unit electronic charge. Yes, correct. So it is less than unit electronic charge. Okay, C is the correct answer. Next, dipole-dipole interaction is stronger than the London forces, but is weaker than ion-ion interaction because, yes, dipole-dipole interaction is stronger than the London forces, but is weaker than ion-ion interaction because, what is the correct answer? Only partial charges are involved. Only total charges are involved. Both A and B. D, sometimes A and sometimes B. It is A. Okay. It is A. So it is only partial charges are involved. So correct answer is A. So because of this, the dipole-dipole interaction is stronger than London forces, but it is weaker than ion-ion interaction because of the partial charges which are involved. Next, induced dipole moment, it depends upon the first dipole moment present in the permanent dipole, second polarizability of the electrically neutral molecules. So identify the correct option. A, 1 is correct but 2 is wrong. B, 1 is wrong and second is correct. C, both 1 and 2 are wrong. D, both 1 and 2 are correct. Yes. What is the answer? Induced dipole moment, it depends upon the permanent dipole as well as the polarizability of the electrically neutral molecule. So it is D. Okay, both 1 and 2 are correct. So it depends on both permanent dipole as well as the polarizability of electrically neutral molecules. Dipole-induced dipole interactions are present in which of the following pairs? Yes, dipole-induced dipole. Now, what is the condition for dipole-induced dipole? One of the molecules should be polar molecule and another should be a non-polar molecule. Okay, so see the examples. Among this, one should be a polar molecule and another should be a non-polar molecule. Yes, what is the correct answer? What is the condition? Dipole induced dipole. So one should be a polar, another should be a non-polar. It is B. Okay, HCl is a polar molecule, He is a non-polar. So correct answer is B. Which of the following exhibits the weakest intermolecular forces? Yes, which of the following exhibits the weaker intermolecular forces? Which of the following? Yes, correct. C. Good. Okay, so it is C. He. So it exhibits the weakest intermolecular forces. So next we'll go for laws. Okay. So next we'll start with the gas laws. So based on the physical properties of gases, okay, there were several researchers or scientists who carried out some experiments, okay, and they proposed some gas laws. Okay, so there was a first scientist called Robert Boyle. Okay, Robert Boyle in the year 1662, what he formulated his law and he gave his name and it was called as Boyle's law. Okay, so what does this Boyle's law tell you? Okay, or what is its statement? So at constant temperature, pressure of fixed amount. Okay, what do you mean by fixed amount, or what is amount? Amount is nothing but it is the number of moles, okay, of a gas. It varies inversely with its volume. So whenever you keep a temperature, so when you are keeping your temperature constant, so what Boyle did, what he did, he kept a temperature constant. So temperature was kept constant. Okay, temperature was kept constant, and he saw what? So a pressure of fixed amount, that is number of moles of gas, varies inversely with the volume. Okay, so it was given as pressure is inversely proportional to its volume. So when you remove this sign, okay, so it will be what? It will remove, that is P is equals to constant. So you have to remove the sign and you get what? Constant. So introduce the constant. Constant, you can take it as K1. Okay, you can take the constant as K1 into 1 by V. Okay, so or PV is equals to constant. When PV is equals to constant, when T, that is temperature, and amount or number of moles are constant. So P1 V1 is equals to P2 V2 is equals to constant. So what it depends? So it depends on the amount of gas. Okay, N is nothing but it depends upon the amount of gas, and what? It depends upon the temperature of gas. So what did Boyle say? So whenever you keep temperature constant, okay, And so it depends on the amount of gas, and if the fixed amount of gas at constant temperature T, if you see that if a fixed amount of gas at constant temperature T will occupy the volume what V1, okay. If you keep temperature T constant at some amount of gas, what will happen? The pressure, it will undergo a change in pressure, that is P1. So upon expansion, so P1, when you apply some pressure, okay, from P it will go to P1, okay, and it occupies the volume V2. So according to Boyle's law, it is said to be P1 P2 is equals to V2 by V1. Okay, so this was introduced by Boyle's. So this is the mathematical form of its law. So Boyle's law. Okay, so this was given by Boyle's. So we'll see the graphical representation of this Boyle's law. Okay, so you can see here. So here the graphical representation is how it is pressure. So pressure is given in bar. Okay, pressure is given, or it is calculated in bar. So it is calculated in bar, and volume dm cube. Okay, dm cube is the unit. So you can see here. So value of constant for each curve. So for each curve there is a value, right? For each curve there is a value. So it is different because for given mass of gas. So for different amount of gas taken, okay, it varies with the temperature. So it varies only with the temperature. So each curve, you can see this each curve, it corresponds to different constant temperature. So, and these are nothing but it is called as isotherm. Okay, each curve, okay, this each curve which is corresponding to different constant temperature is nothing but your isotherm. Okay, so higher curves. So this this one is a very higher curve. So higher curve means what? It is having a higher temperature. So for given amount of gas, okay, as you vary the amount of gas, so it will give different amount of temperature. Okay, and the highest curve, this highest curve, what it determines or what it corresponds to higher temperature. So 600. So this is the higher temperature. Okay, so these are nothing but it is called as isotherm. So these are different curves, okay, which are at different temperature, constant temperature, is known as the isotherms. Okay, next was Charles' law. So this was Charles' law. So what was the statement of Charles? So for a fixed mass of gas at constant pressure, okay, at a fixed mass of gas at constant pressure. So what was kept constant? Pressure was kept constant. What was kept constant? Pressure was kept constant. Okay. Then what happens? Volume of gas. So volume of gas directly increases with the increase in temperature, okay, or decreases on cooling. So this was the statement given by Charles. So what did Charles say? So for a fixed amount of gas, so when you fix the amount of your gas, so when you fix the amount of gas at constant pressure, when you keep this pressure constant, what will happen to the volume? So volume of gas will increase with the increase in the temperature. If you decrease the temperature, it will cool. Okay, so it decreases on cooling. So he found that for each rise in temperature, okay, for each degree rise in temperature, volume of gas increases by, how it increases? 1 by 273.15. Okay, for each degree rise in temperature, the volume of gas, it increases by 1 by 273.15 of original volume of gas. So V is directly proportional to T. If you remove this proportionality constant, okay, you have to introduce a proportionality sign. If you remove, okay, you have to introduce a constant. So V by T is equals to K, or it is constant. So after solving, it comes by V1 upon T1 is equals to V2 by T2. Okay, absolute zero temperature. Absolute zero temperature is what? When you take it in Kelvin. Okay, 273. 273 is nothing but it is in terms of Kelvin. So absolute zero temperature. Where zero temperature is nothing but 273 Kelvin. So every rise in each degree rise in, what did Charles say? For each degree rise in temperature, the volume of gas, it increases by 1 by 273.15 of original volume of gas at 0 degree. So now here, okay, you can see this graph. The graph was plotted against volume against the temperature. Okay, so here the each line, what it corresponds, it is said to be isobars. Okay, each line of volume versus temperature is said to be what? It is said to be isobar. So at minus 273.15 degrees Celsius, gas will not exist. Okay, gas will not exist, but gases get liquefied. So gases will get liquefied before this temperature is reached. So this was the law and mathematical statement given by Charles. Next is Gay-Lussac's law. So the next law was Gay-Lussac's law. So Gay-Lussac's law, what it says, so that pressure is at constant. So what is kept constant here? Volume is kept constant. Okay, so volume is kept constant. So here volume is kept constant. Okay, so at constant value, what happens? So pressure of fixed amount of gas, it varies directly with the temperature. So here pressure is directly proportional to temperature. Okay, at fixed amount of gas, when you keep volume constant. So P by T, if you remove the proportionality sign, you will introduce a constant. Okay, so each now, so after solving, you get P1 by T1 equals to P2 by T2. So this is the temperature on absolute scale. So this is based on the absolute scale. So when Gay-Lussac, he drew the graph, okay, of pressure versus temperature. So here, like this lines were obtained. So these, each line is nothing but it is called as isochore, okay, isochore. So this is nothing but your, it represents your Gay-Lussac's law. So next is Avogadro's hypothesis. So what is Avogadro's hypothesis? So the statement is as follows. So for similar values of pressure and temperature, okay, for similar values of pressure and temperature, equal number of molecules of different gases will occupy equal volume. Means what? So here the pressure and temperature, okay, pressure and temperature is kept constant. So for so your volume is directly proportional to amount of gas. Okay, so if you remove this proportionality constant, it will be constant, okay, proportionality constant into n. Okay, you can take constant as k. So therefore, since what will happen here, so volume of gas is directly proportional to number of moles. Okay, so each mole, 1 mole of each gas at HTP. What do you mean by HTP? HTP is nothing but standard temperature pressure. So what is the standard temperature? Temperature is 273.15 Kelvin. What is the pressure? Okay, the pressure is 1 bar, or it is 10 raised to 5 pascals. Okay, it is 10 raised to 5 pascals. Or if you want to write in degree, it is 0 degrees Celsius. So this is, so for 1 mole of each gas at HTP, it will have same value of standard temperature and pressure. Okay, so this is Avogadro's hypothesis. What it states that at constant pressure and temperature, equal number of molecules of different gases will occupy equal volume. Okay, so volume is directly proportional to amount of gas. So this is this was said by Avogadro's hypothesis. So next we'll see ideal gas, combined gas, and Dalton's law. What is ideal gas equation? So how do you get ideal gas equation? From Boyle's law. So when you take all the mathematical statements from Boyle's law, Charles' law, and Avogadro's law, you get V is proportional, V is this to N by T by P. Okay, so when you remove this proportionality sign, you get PV is equals to nRT. PV is equals to nRT. So, so here you are introducing R. Okay, what is this R? R is nothing but universal gas constant. So universal gas constant. So this is called as ideal gas equation. So PV is equals to nRT is nothing but your Avogadro. This is your ideal gas equation. How you get it? You get it by combining your Boyle's law, Charles law, and Avogadro's law, not Gay-Lussac's law. Boyle's law, Charles law, and Avogadro's law. When you combine, you get PV is equals to nRT. What is R? R is nothing but your universal gas constant. Okay, remember this. So this is your ideal gas equation. PV is equals to nRT. So next, what is the value of R? Okay, 0.0821 liters ATM, okay, per Kelvin per mole, then 8.314 joules per Kelvin per mole. So this is with respect to different units. Okay, so these are the 4 different types of values for R in different units. So how do you calculate the density of gas? So from ideal gas equation, if you this, what is density? Density is nothing but mass by volume, right? So when you substitute what is mass by volume, you get the final equation as in PV is equals to nRT. When you substitute this, you get density is equals to PM by RT. Okay. So this is your density of gas can be calculated by this particular formula. Now, what is combined gas law? What do you mean by combined gas law? If temperature, volume, and pressure of a fixed amount of gas vary from T1, V1, and P1 to T2, V2, and P2, then we write, okay. So how do you write P1, V1, T1? Okay, is equals to NR, and P2 and V2 in divided by T2 is equals to NR. So you just substitute and you get what P1 V1 upon T1 is equals to P2 V2 into T2. So this is nothing but combined gas equation. So it is the amount or you are calculating the different temperatures, volume and pressure for fixed amount of gas which varies. Okay, it varies from T1 to T2, V1 to V2, and P1 to P2. Then you have to you get this combined gas equation. So remember what is the last remember this particular for combined gas. Okay, it is P1. So it is what P1 V1 V1 by T1 is equals to P2 V2 by T2. So this is a combined gas equation. So remember this last. Next is Dalton's law of partial pressures. Okay, so what was so this was given by Dalton, okay, in the year 1801. So what did he give, or what was his statement? So at a given temperature, the total pressure of a gas mixture, okay, at a given temperature, the total pressure of a gas mixture is equal to sum of the partial pressure which is exerted by each individual gaseous component. So how it is given? So partial pressure of one component is mole fraction into its total pressure. Okay, so P is equals to pressure is given as psi into P total. So this is the this partial pressure, how you calculate. Okay, so when you want to calculate the partial pressure of one component, you have to calculate it by mole fraction into the total pressure. And if P1, P2, and P3 are partial pressures of each components, okay, 1, 2, 3 respectively, then how do you add, or how do you take the this total pressure? Total pressure is equals to P1 plus P2 plus P3. Okay, so this is how you are going to find the partial pressure. So when you want to find the partial pressure of one component, remember mole fraction into total pressure. This is the formula which is used. And if you want to find out the sum of all the partial pressures, then it is P total is equals to P1, P2 plus P3. Okay, and so on. So this is the Dalton's law of partial pressure. So based on this, we'll solve some questions. So 600 cc of a gas at pressure of 750 mm of Hg is compressed to 500 cc. Taking the temperature to remain constant, the increase in pressure is, okay, so what is given here? What is kept constant? What is temperature is kept constant. Okay, temperature is kept constant. So what it is? Okay, so P1 V1 equals to P2, V2. Okay. So now pressure. What is the pressure? So it is 750. So 750 mm of Hg is been compressed to 600. Okay. V1 of one particular gas. Then what is happening? So what will be the increase in pressure? So you have to find what is the increase in pressure when it is compressed to 500. So further this V1 is compressed to 500. So it is like this. So how much you get? So P2 is equals to 900, right? 900. So increase in pressure. How do you calculate increase in pressure? Increase in pressure, okay, is given by P2 minus P1. So P2 is how much? P2 is 900 and P1 is 750. So the correct answer is 150 mm. Okay, so like this, you are going to find out the increase in pressure. So this is the correct way of solving. Next, 900 ml of nitrogen at 27 degrees Celsius is cooled to minus 5 degrees Celsius at the same pressure. Okay, the new volume becomes. So how to solve this? Yes. So what is V1? V1 is given as 500 ml. Okay. Then what is T1? So temperatures are here given in degrees Celsius. So we need to convert them into Kelvin. So plus 273. How much you get? You get it as 300 Kelvin. Then T2. It is cooled to T2. T2 is minus 5 plus 273 equals to 268 Kelvin. Okay. Then what is volume? V2 we have to find. So it is V1 by T1 equals to V2 by T2. Okay, use this. So what you want to find? We want to find V2. So V2 is equals to V1 T2 by T1. Yes, substitute and see what you get. So 500 is V1. What is T2 is 268 divided by T1 is your 300. How much you get? Just see. What will be the answer? What is your V2? It is 446.6. Okay, solve this. You will get the answer B. So like this, you're going to solve. Okay. So based upon the gas laws, different mathematical, this you're going to solve it. So next is for an ideal gas. Okay, for an ideal gas, number of moles per liter in terms of its pressure P, gas constant R, and temperature T is. Okay, now here how to solve this. So for an ideal gas, number of moles per liter in terms of its pressure P, gas constant R, and temperature T is. So what is ideal gas equation? Ideal gas is PV is equals to nRT. Okay. So what we have to find? We have to find number of moles per liter. Okay. Number of moles per liter is nothing but your N by V. What you can write? So PV is equals to nRT. So take this P, you shift it there. So it will be P by RT. Okay. So N by V is nothing but number of moles per liter, right? Volume will be in per liter. So is equals to what is answer? P by RT. So the correct answer is P by RT. So for an ideal gas, when they have asked you to find the number of moles per liter. So you have to take what? This V, just shift it. Okay. And you get, so number of moles. N is nothing but it tells you about number of moles, right? Amount of gas. So it is number of moles per liter. Volume will be in liter. So is equals to P by RT. So it is, they have asked you in terms of pressure, gas constant R, and temperature T. So it is, the correct answer is C. Next, if 2 moles of an ideal gas at 546 Kelvin occupy a volume of 44.8 liters, the pressure must be. Okay, so how to solve this? So what they have asked, 2 moles of ideal gas at temperature is given. Okay, temperature is given, number of moles are given, then what volume is given. So we have to find the pressure. So PV is equals to nRT. Just substitute and see what you get. PV is equals to nRT. So what you have to find? You have to find the pressure. So pressure is equals to nRT by V. Solve it. You know all the terms. So 2 into R is what? 0.0821 into 546. Temperature is given in Kelvin, so no problem. What is volume? 44.8. What you'll get? Just see. What is the answer? By substituting, what will be the pressure? Pressure will be in terms of atmosphere. Okay, ATM. It comes to 2. Okay, 2 atmospheric pressure. So B. B is the correct answer. So B is the correct answer. Next, the pressure and temperature of 4 dm cube of carbon dioxide are doubled. Okay, so pressure and temperature of 4 dm cube of carbon dioxide are doubled. The volume of carbon dioxide gas would be. So we had seen this particular. Okay, so it is what? P1 V1 upon T1 equals to P2 V2 by T2, right? From combined gas equation. So what you have to so what they have said, the pressure and temperature of 4 dm cube of car are doubled. So if P1 is equals to P and T2 is equals to T, then if it is double, so P2 will be what? It will be 2 times P, and T2 will be, it will be 2 times T. Why? The pressure and temperature are said to be doubled. So if you consider this, and what is volume given? Volume is given as 4 dm cube. Okay, so substitute how it will be. So pressure, okay, P1 is what? P. What is V1? V1 is equals to 4 divided by what is T1? T1 is your So T1 is your T. Okay. Then equals to what is your P2? P2 is 2P. Then what is your V2? V2 we don't know. So keep it V2. And T1 is equals to 2 times T. So you can see clearly that V2 is equals to 4. So there will be no change in volume. So no change in volume. So the correct answer is C. So it is C. So you have to just, okay. So pressure, just relate it. So V2 is nothing but it is 4. So there is no change in volume. So the correct answer is C, 4 dm cube. Hydrogen diffuses 6 times faster than the gas A. Okay. The molecular mass of gas A is. So your rate of diffusion. So there is a formula of rate of diffusion. So take it out. So rate of diffusion for H2. So 2 gases are given. One is hydrogen and another is a ideal gas. So rate of diffusion of H2 gas by R gas is given by square root of molecular weight of molecular mass of gas versus molecular weight of the H2 gas. Okay. So what is given? It is 6 times faster, right? It is 6 times faster than gas 1. So take it as 6. So this is given as 6. So hydrogen diffuses 6 times faster than, so R by H2 by R by gas is given as 6 equals to then square root of. So take this square root, shift it this side. So you get M gas equals to, so this becomes square root of 6 becomes 36. So 36 into what is molecular mass of hydrogen? When you substitute molecular mass of hydrogen, it will be 2. So into 2, you will get it as 72. So the molecular mass of gas is 72. So the correct answer is A. Okay, square. What I've done here, I've shifted this square root here. Okay, square root has been shifted. you add the square root to 6 also, so you get 36. And what is mass or molecular mass of hydrogen is 2. So when it goes this side, it will multiply, it will be 72. So A is the correct answer. So 28 grams of each, okay, 28 grams of each of the following gases are taken at 27 degrees Celsius and 600 mm pressures. Which of this will have the least volume? Okay, so what is given here? So 28 grams of each of the following gases are taken at 27 degrees Celsius. So which are the gases? HBr, HCl, HF and HI. So from your Avogadro's Avogadro's hypothesis, what it says, that volume is directly proportional to amount of gas, right? So at what? At constant temperature and pressure, right? At constant temperature and pressure, volume of gas is directly proportional to N. So as we know, how is N given? N is given by mass of the gas upon molecular weight. Okay. So when N will be least, when molecular mass will be more. So what they have asked, when you have the least volume. So among the following gases, you have to tell which of this will have the least volume. So when N will be least, okay, that time M should be higher. So which will have a more mass here? Which will have a more mass? It will be iodine, right? Iodine will be having the higher mass, right? As you go down the group, what will happen to the size? So iodine, the size will be more. So iodine, it has a molecular weight is more. So it is D. So you have to compare. So amount of gas, okay, it is given as what? It is mass of the gas upon molecular weight. So if N is least, this molecular weight should be, if N should be least, molecular weight should be highest. Okay, it should be more. So as it is inversely proportional. So HI is the correct answer. D is the correct answer. The mole fraction of dioxygen in a neon dioxygen mixture is, okay. So here what they have given, the mole fraction of dioxygen in a neon dioxygen mixture is 0.18. If the total pressure of the mixture is 25 bar, the partial pressure of neon in the mixture would be. So we have seen from partial pressure, okay. So the individual partial pressure as well as the total pressure formula was given. So you have to first find. So what is given here? First, they have given you the this what mole fraction of dioxygen is given and the total pressure is given. So first we have to find what? You have to find the mole fraction for your neon. Okay, how it will be? It will be 1 minus psi O2. Okay, so what it will be? 1 minus 0.18. So what you get? This is a mole fraction for your neon. So it is 0.82. Okay, this is mole fraction of your neon. Now, how do you find the partial pressure? So partial pressure of one component is given by what? It is the mole fraction into total pressure, right? So partial pressure of neon is equals to X Ne plus partial total pressure. Okay. So it will be what? What is the neon? It is 0.82 plus what is the total pressure? It is 25. So it is 20.5. Okay, it is 20. Just a second. So when you're finding the partial pressure of neon, it is psi of Ne. Okay, partial pressure of Ne into total pressure. So it is 0.82 into 25. It comes to 20.5 bar. So this is the partial pressure of neon. Okay. So what is the partial pressure of neon in the mixture? So it is 20.5. So the correct answer is D. So first, so what is given here? Dioxygen is given. From that dioxygen, you know the this also. Okay. So mixture is given. So you have to calculate the mole fraction for neon first, and then you have to find out the total pressure. The total pressure is also given, so you have to find the pressure on the neon. So that is psi Ne into P total. So this is the way you have to find out the partial pressure for answer for problem. Okay. Next is kinetic energies and velocity. So kinetic energy or kinetic gas equation is given by P is equals to 1 by 3 mn c square divided by V, where m is the mass of each molecule of the gas. N is what? N is the molecules, number of molecules of the gas. C is the root mean square, okay, velocity of gas, and V is the volume of container. So remember this kinetic gas equation, it is nothing but P is equals to 1 by 3 mn c square divided by V. And these are the entities, what they are called. Okay. Next, root mean square, that is RMS or velocity, is given by C is equals to root of C1 square plus C2 square plus C3 square till Cn square divided by N. So like this, you have to calculate your RMS. Okay, that is your root mean square velocity. So you have to add it, you have to take the square root and you have to add all and divide it by the number of this, okay, N. So where C1, C2, C3 till Cn, these are called the velocities of 1, 2, 3 respectively till the 9th molecule. So C is equals to, how it is given, square root of 3RT. Okay, 3RT by M, capital M. Capital M is what? Your molecular mass. This RT, this can be replaced as PV also, because PV is equals to nRT. So it is given as square root of 3 into PV by M. Now this volume by mass, okay, volume by molecular mass is nothing but your density. So square root of 3P by D. So this is the substitution. So they have further simplified it. Okay. So what is average velocity? So average velocity is nothing but it is the average of speeds of different molecules in a gas at a particular temperature. So how do you calculate the average velocity? So it is V is equals to V1 plus V2 plus V3 up till Vn divided by N. So it is given by square root of 8 RT by pi M. Okay, remember this, how to find the average velocity. The final, this you remember. So it is square root of 8 RT divided by pi into M. Next is most probable velocity. Okay, most probable velocity is nothing but it is a velocity possessed by maximum fraction of gas molecules at given temperature. So it is V dash is given by square root of 2RT divided by M. So how do you take the relation between this different types of velocity? Okay, most probable velocity is given by square root of 2. Average velocity is square root of 8 by pi, and root means square root. Velocity is root of 3. So when you take the approximate of this, so it is 1 is to 1.128 is to 1.224. So this is a relationship between the different types of velocities. Then what is kinetic energy? So when you're finding out the kinetic energy per mole, okay, it is 3 by 2 PV. So PV is nothing but your RT. So it is further simplified as 3 by 2 is equals to RT. So when you're finding it for per molecule, okay, per molecule, you have they have introduced the Avogadro's number as well as the K. K, K is nothing but your Boltzmann constant. So 3 by 2 RT by N is equals to 3 by 2 KT. KT, K is what? Your Boltzmann constant. T is your absolute temperature. Okay. So this is when you're finding per mole, this is the equation. When you're finding for per molecule, this is the particular equation. Okay. Now, we'll solve a question on average kinetic energy. So as the temperature is raised from 20 degrees Celsius to 40 degrees Celsius, the average kinetic energy of neon atoms changes by a factor of. Okay, how does it changes? So kinetic energy is given as our kinetic energy is equals to 3 by 2 RT. Okay, 3 by 2 RT, or kinetic energy is what? Kinetic energy is directly proportional to temperature. So kinetic energy what is the temperature? It is 40 degrees Celsius. Okay, divided by kinetic energy 20 degrees Celsius is equal to temperature 40 degree divided by temperature 20 degree Celsius. Okay. So when you this what you do, 40 plus 273 and 20 plus 273 added by temperature, what you get? You get 313 divided by 293. So this is nothing but your kinetic energy. So kinetic energy is related to temperature. It is directly proportional. So you have to add the absolute temperature. So you have to multiply it by the absolute temperature, that is 273. You get this particular answer. At the same temperature, calculate the ratio of average velocities of SO2 to CH4. Okay, so you have to calculate the average velocity. So there are two gases given. One is sulfur dioxide and one more is methane gas. So how do you calculate it? Okay, the average velocity. So average velocity of is directly proportional to, or it is inversely proportional to the molecular mass at constant temperature. So what is kept constant is your temperature is kept constant. So this what average velocity of what you take SO2. So you have to find the ratio. So average velocity of CH4. Okay. So that is what it will be. So molecular mass of CH4 divided by molecular mass of SO2. So what is V average of SO2 divided by V average of CH4? So what is the molecular mass of CH4? CH4 is 16, right? C, carbon is 12 and each hydrogen 4. So it will be 16. Then SO2 is 64. So take out the square root. So it will be square root of this is 1, 4. Okay, and this is 4. So it is 1 by 2. So the ratio is 1:2. So the correct answer is C. So like this, you have to calculate the average velocity. Okay, so they have given two gases. So you have to take the average velocity. You know that average velocity is inversely proportional to its molecular mass. So substitute in that way and you get this particular answer. When the temperature of an ideal gas is increased from 27 degrees Celsius to 927 degrees Celsius, the kinetic energy will be. Okay. So you know what is kinetic energy? Kinetic energy is directly proportional to temperature, right? So kinetic energy is directly proportional to temperature. So your kinetic energy T2 by kinetic energy of T1, right? So the energy is increased. It is equals to how it is given by T2 by T1. Okay. So what is the kinetic energy? It is 9. Okay. T2 is what? It is 927 plus 27 degrees Celsius, right? 27 degrees Celsius is what? What is a T2? It is changing from an ideal gas. When a temperature of an ideal gas is increased from the from 27 degrees Celsius to 927 degrees Celsius, the kinetic energy will be. So what it will be? So 927 plus you have to add it with the absolute temperature divided by, so 27 plus 273. Okay. So you get 1200 divided by 300 Kelvin. Okay, you are adding it with the absolute temperature. Absolute temperature is nothing but your 273 Kelvin. So how much you get? You get it 4. So Ke, okay, kinetic energy T2 is 4 times that of kinetic energy T1. So it is 4 times. So the ideal gas is increased from 27 to 20 this. So the kinetic energy is 4 times that of T1. Okay, so this is the kinetic energy equation. So van der Waals equation for real gas is nothing but P plus N square A by V square. Okay, V minus NB is equals to nRT. So your A and B are nothing but they are van der Waals constant. So what does A signifies? A signifies that larger, that is the greater the value of A, larger are the intermolecular forces of attraction. And what does B signifies? B signifies that its value is a measure of effective size of gas molecules. Oh, okay. So it signifies the effective size of the gas molecules. So this is nothing but your compressibility factor. Okay, compressibility factor is nothing but when your ideal gas it deviates. Okay, it deviates. So it is given as compressibility factor. So compressibility factor for real gases, it is never equal to 0, and for ideal gases it is equal to 1. Okay, ideal gases are not true. Okay, real gases are true in nature. So this is the what is that? If Z is greater than 1, it is nothing but it is a real gas is greater than V ideal. Okay, so when Z is compressibility factor, Z is nothing but your compressibility factor. So these are the different points. Okay. So, according to kinetic gases of theory, in an ideal gas, between the two successive collisions, a gas molecules always travels in what? The gas molecules, whenever there is collision between the two successive lines, it will always travel in a straight line. Okay, it will always travel in a straight line. In Van der Waals equation of state of the gas law, the constant B is, what does B tells you? What does B tells you? B tells you what? It tells you about the volume occupied by the molecules. Okay, so C is the correct answer. What is the correct answer? It is C. Okay, volume occupied by the molecules. So it tells you about the volume occupied by the molecules. The term that corrects for the attractive forces present in the real gas in the Van der Waals equation is, so Van der Waals equation, it tells, it depends upon AN square divided by V square. Okay, so this is B. So B is the correct answer. Okay, so by this we have solved some of the important questions based on states of matter. Okay, thank you students for answering. So we'll meet in tomorrow's class.